The ionization of a weak monoprotic acid HA in water is represented by HA reacts with water to give hydronium ions and its conjugate base A-. Ka is equal to hydronium ion concentration times A- concentration divided by HA concentration. Ka is a special case of the equilibrium constant Kc and is called the acid ionization constant. Instead of the subscript C, the letter A for acid is used. Recall that water is a pure liquid, so it doesn't appear in Kc and Ka. The larger the value of Ka, the stronger the acid. Both hydrofluoric acid and acetic acid are weak acids, but hydrofluoric acid is a stronger acid than acetic acid, as hydrofluoric acid has a larger Ka value. Notice they both have the same concentration of 0.10 molar here, but they don't have the same pH. Since HF ionizes more than CH3COOH, HF has a lower pH than CH3COOH. Here are some acid ionization constants, Ka, of some weak acids. Their Ka values are all less than 1. You are not required to memorize them. Notice among these weak acids are the carboxylic acids, chloroacetic acid or chloroethanoic acid, formic acid or methanoic acid, benzoic acid, and acetic acid or ethanoic acid. Notice too that the Ka value of phenol is much smaller than the Ka values of the carboxylic acids. Take this as evidence to support the idea that phenol is less acidic than carboxylic acids in Chapter 6. Here is an example. Calculate the pH of a 0.50 molar HF solution at 25 degrees Celsius given its Ka at that temperature is 7.1 times 10 to the power of negative 4. First, recall that HF is a weak acid. Now, even if you have forgotten this, you should notice that the Ka value is smaller than 1. This verifies that HF is a weak acid. This means that HF is not completely ionized in solution, so only a part of the 0.50 molar solution of HF becomes hydronium ions and fluoride ions. How much will ionize? We don't know, so we use the ice table. At the start, there is only unionized HF, so its initial concentration I is 0.50 molar. There are no hydronium and fluoride ions, so we write 0 molar for each at the start. Since hydronium and fluoride ions are missing, the system wants to bring them into existence. It calls upon HF molecules to sacrifice themselves to react with water to produce hydronium and fluoride ions. So for the change in concentration C, we write minus X for HF and plus X each for hydronium and fluoride ions. To get the equilibrium concentrations E for each species, we add the entries of I and C. Thus, 0.50 plus negative X gives 0.50 minus X for HF. 0 plus X gives X for both hydronium and fluoride ions. We write the Ka expression, which is equal to hydronium ion concentration times fluoride ion concentration in the numerator. Hydrofluoric acid concentration is packed in the denominator. We equate this to the Ka value, which is given as 7.1 times 10 to the power of negative 4. We now substitute every species' equilibrium concentration expressed in terms of X into the Ka expression. Then we solve for X. Like before, when Kc is small, we use the approximation method. Since Ka is 7.1 times 10 to the power of negative 4, which is smaller than 0.001, Ka is considered small. If Ka is small, it implies that the numerator is small and the denominator is big. A small numerator means hydronium and fluoride ion concentrations are low. The denominator is the concentration of unionized HF molecules. If it is bigger than the numerator, it means that there are quite a lot of these molecules in solution. This means that the equilibrium position is closer to the left, that is, favoring the reactant HF. There should therefore be fewer products, that is, there ought to be little hydronium and fluoride ions at equilibrium. Thus, for all of this to hold true, x is necessarily small compared to 0.50. 0.50 minus x is therefore approximately 0.50. Once we make this approximation, the number of steps for solving x is reduced. Do not stop at x. We need to interpret what x is. Return to the ice table. X happens to be the hydronium ion concentration. One more step. Substitute X, that is the hydronium ion concentration, into the pH formula to get 1.72. We have seen that the acid ionization constant Ka gives us an idea of the strength of an acid. There is another way to determine the strength of an acid. It is percent ionization, which is a quantitative measure of the degree of ionization. In this example, after using the ice table for the weak acid benzoic acid and solving for X the usual way, we can find percent ionization. The formula for percent ionization is hydronium ion concentration at equilibrium divided by the initial unionized acid concentration. In this case, it is that of benzoic acid at the start, multiplied by 100%. So substitute the correct values from the ice table to obtain 2.5%. Essentially, we compare the hydronium ion concentration at equilibrium with the initial unionized acid concentration and express this as a percentage. Here is an example. Determine the pH and percent ionization for 0.15 molar acetic acid solution at 25 degrees Celsius, given that the Ka for acetic acid is 1.8 times 10 to the power of negative 5 at 25 degrees Celsius. Recall that acetic acid is a carboxylic acid, so it is a weak acid. If you don't remember this, look at the Ka value. It is smaller than 1, so acetic acid must be partially ionized in solution. That is, it is a weak acid. Next, we construct the ice table and complete it. Solve for X, which is the equilibrium concentration of hydronium ion. We use pH is equal to negative log of hydronium ion concentration to find pH. Finally, we input the appropriate values into the percent ionization formula, which is equal to the hydronium ion concentration at equilibrium divided by the initial unionized acid HA concentration times 100%. To solve for X, we need to write the Ka expression, which is hydronium ion concentration times acetate ion concentration divided by acetic acid concentration. Equate this to 1.8 times 10 to the power of negative 5, which is given. Plug in the equilibrium concentrations of each species from the last row of the ice table. Since 10 to the power of negative 5 is small, we use the approximation method. That is, since Ka is less than 0.001, X is small relative to 0.15. So the denominator is approximately 0.15. Solve for X, which is the hydronium ion concentration. We are not asked for this. We are asked instead for pH and percent ionization. So we substitute 0.00163 molar into the formula. pH is equal to negative log of hydronium ion concentration to get 2.78. Finally, to get percent ionization, we substitute the hydronium ion concentration at equilibrium, that is, the value of X, and the initial concentration of the unionized acetic acid into the formula to get 1.1%. Diprotic and polyprotic acids undergo successive ionizations, losing one proton at a time, with each having a Ka associated with it. The example shown here is that of weakly acidic carbonic acid. In the first stage of ionization, carbonic acid becomes hydrogen ion and hydrogen carbonate ion. Ka1 is the acid ionization constant representing this first ionization. It is hydrogen ion concentration times hydrogen carbonate ion concentration divided by carbonic acid concentration. The hydrogen carbonate ion then proceeds to ionize in the next step to give hydrogen ion and carbonate ion. Ka2 is the acid ionization constant representing this second ionization. It is hydrogen ion concentration times carbonate ion concentration divided by hydrogen carbonate ion concentration. Ka1 is greater than Ka2. For a given acid, the first ionization constant is much larger than the second, and so on. This is because it is harder for a negatively charged species to lose H+. After it does so, it gets a double negative charge, which is not so desirable.